Great. So last time actually we talked about game theory and some motivation for that and some like basic things about it, like uh, multi-trillion dollar business of advertisement actions, let alone healthcare market and lots of other stuff. So it's like a very huge market. And if you understand them well, then you can actually do a lot because a little bit saving or a little bit more efficient mechanisms actually can cause a lots of saving or profit for a company. And also we played at the end of the class, I mean, some simple game. And that simple game was chocolate game that has been changed to carrot game, essentially. And we had actual carrots in the piece. So we had some discussion about that and see that just a little bit changes in the assumptions, changes the whole outcome of the game. And the people may play differently. So any small thing matters. And lots of the things actually goes toward understanding better the games and the way that we can formulate these games. And almost all of them, there are lots of math involved. So math would be, I mean, critical things. For example, all this, you will see this sponsored product at Amazon or like Google ads, etc. All of them, lots of math are involved essentially. Who is the person selected and who is the advertisement which is selected to show in a particular ad and how much should we charge that advertisers, etc. Lots of algorithms and also heavy backends, essentially. But to start with that, we will start with some of the basic things that we need to learn about them for game theory, and we talk about it. This is an introduction to probability theory, and also we will talk today and next session about probability theory, and another session we will talk about linear programming. Again, please mute yourself if you don't want to talk to avoid noises. And good. So, and these are like two very basic things that we need essentially for game theory that we will talk about them. And later, and then we will continue with the continuation of the regular, I mean, discussion of the games, normal form games and equilibrium stuff and lots of other stuff. And also this, you can also take a look at them at my other class, Introduction to Algorithms. These are available for probability theory. You can just take a look at them as well. And good. So let's go to the things. So we will first start with basics of probability theory. We talk about Bayes rule, which is a very important thing. This is actually something which is used a lot in A/B testing. And A/B testing, I will talk a little bit about it, but you can read about them a lot. This is something I'm not so sure that I mean, we may have a limited courses in university talking about it, but like in industry is a very big thing because all of this you need to know that, I mean, if you are creating a new website, because it is better than the previous one or not. And generally you need to send some traffic to this website, but you don't want to send a lot of traffic because you don't know what are the what would be the outcome. And we are talking about the big tech, so I mean, or big companies, that a little bit of traffic means, I mean, if you send it and you miss it, it would be in the order of thousands, if not millions of dollars, essentially, difference if you send it to the wrong website or the website is not doing this. So it's super important. It's very important to use lots of probability theory, actually, to make sure that there is no biases, there is no issues, and everything is fine, essentially. Good. So, good. So, yeah, so Bayes rule and particular probability theory is very important. to learn about them and use them. And this is some knowledge that if you increase your knowledge, that would be great. And then we talk about random variable and distribution. That's another thing, that everything that we talk about here would be about joint distribution, etc. And it is important that you know about them. And this is just a crash course. I mean, you should go and actually read much more about them. And there's a lot of, I mean, exercise that you need to do that. Several places like big companies generally also, if you have an interview, etc., they have a lot of emphasis on this concept. So you need to read these materials and learn them quite well. Good. So here, let's start with decrease the size. Wait. Let's start with the definition of probability theory. So generally, when we talk about probability theory, we are talking about some experiments. So experiments, I mean, can be anything, but a simplest one can be toss a coin, for example, once or twice. Generally, we have some space sample of spaces. This one. So we have some sample space. Sample space means essentially all possible outcomes that can exist. For example, if we have a coin and we will toss it twice, we can have head, 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 tail, tail, head, or tail, tail. Event would be a subset of all possible outcomes, like head, head, just with one event A, or it can be another event B, which is head, tail, and tail, head. So that's all possibility. So, and this is very important. We try to make sure everything is like as simple as and as formal as possible. That's the whole idea that we are talking about. It is not just something, I mean, obscure that you don't know what's going on. No, everything is very simple. And these are all coming from some axioms of probabilities. These are the three important axioms of probability. Almost everything that you will see, it is built on these three axioms. There might be, of course, there might be some complicated theorems, etc., but those theorems also are built on this. And of course, we need to know some of those probability theory stuff and those theorems, such that we can prove the stuff much easier and much faster. But at the end, everything comes from these three things. So it is nothing essentially like hidden or something like that. These are all three things. So this is a probability of A, which is the probability which is assigned to an event A or event B or anything. Should satisfy these three properties. The first axiom is that the probabilities are all between 0 and 1. So the number probability of A, that is, this is a function essentially that gets a set as an input and gives essentially a number between 0 and 0, 1. The second axiom is that the probability of S is equal to 1 and probability of empty set is equal to 0. S means essentially the whole sample space. Again, that makes sense because one of the things in the sample space should happen. Otherwise, what do you call it sample space? And if there is nothing, then probability of empty set should be 0. And last but not least, for two events A and B, probability of A union B should be equal to probability of A plus probability of B minus probability of A intersection B. And again, note that A and B are just sets or subsets. So we can define all these three. So let's, check about this. The first, then after these axioms, we have the proposition. Proposition generally means simple lemmas, but still they need a proof essentially. So we have proposition, then we have lemma or claim, and then from there essentially we have theorems. Generally are the more substantial math, and they need more substantial proofs. Great. So let's start with the first one and see, do you have any ideas that how can we prove the first one? Probability of not A. Not A means essentially the complement of A. Comparing to, essentially not A means S minus A is equal to 1 minus probability of A. Good. So yeah, as it mentioned, so to do that, essentially we can use this axiom to prove the proposition one, this one. We can just essentially consider, as I mentioned, we can consider here A and A bar, or I will say A tilde. So, define that A tilde is equal to S minus A. So that is by definition, if we are using axiom 3 here, then probability of A and A bar or A tilde would be probability of A plus probability of this would be A bar or A tilde minus the probability of A intersection A tilde. So here by definition, by this definition, we know that this is the probability of this would be essentially, so this would be empty set. And now we are using axiom 2 that we know that because probability of empty set is 0, so this would be 0. So the whole thing will be canceled out. Also, we know that probability of the A union A tilde would be S. Again, we are using axiom 2 here. We know that this side would be 1. So we know that 1 is equal to probability of, so what is this one? So we know that 1 is equal to probability of A plus probability of A tilde or A bar. So then you can just, essentially bring probability of A bar to the other side and 1 to other side, and then we will get this one. So it's simple algebra. So everything comes from this simple formula. Now, let's go and talk about the second proposition. So we want to say that for every sequence of disjoint event means that these events as sets, they don't essentially have an intersection with each other. Probability of unit. Oh, this is also very important thing that we are using that. So this notation of sigma, we are using sigma I, means that essentially summing up over all I. Or somehow we are using pi. Pi I means essentially, this means sum of product of all AIs. This essentially means sum of all AIs. And then we have this union and intersection. This means essentially, so this means A1 union A2 to AN. Sometimes we will say the index I equal to 1 to N. But if we don't say that, it means that essentially union of everything. You can similarly define the intersection of everything else. So this is a typical notation that we are using for non-binary cases. So here, we said that if these are disjoint events, disjoint means essentially as a sets, they don't have any intersection. They don't have any intersection in outcomes. Then probability of union of all AIs is equal to sum of the probability of AIs. So essentially, in some sense, we can take the union of all of them. It turns into, the probability of union becomes sum of probabilities. That's the thing that you can say. And see, what can we do for good? So as I mentioned, induction is very important, and you should go and learn about it specifically in the 2-3 lectures of Introduction to Algorithm course that I have it at YouTube. So here we need to use induction. So what is the induction? So induction has two parts: the base of the induction and essentially induction hypothesis and or induction step essentially. So we want to say that so we have A1 to AN, and we want to say first essentially the basis of induction for I is equal to 1, it is true essentially. So this is the basis of the induction. And this is, we say, essentially. And the induction hypothesis here that we are talking about it is that we are saying that if it is correct for I, let's say correct here, correct for N, we want to say then correct for N plus 1. Good. Here, so correct for N. What's the meaning of, I mean, like, let's do that essentially. Here we are talking about N. So for N equal to 1, essentially what does it say? Is that probability of the union of A, I equal to 1 would be just probability of A1 is equal to sum of the I equal to this. So it is probability of A. So that is essentially the basis of induction. And this is like trivial. Generally, I mean, it should be trivial. Now, the main part is the induction hypothesis. That is that it is correct for, so if we have N sets, it is correct. Now, what about if we have N plus 1 sets? And it is important. You should, this is, again, we will discuss that one on those lectures about inductions, that you should not consider your particular A1 to AN and then add AN plus 1. You should start from A1 to AN plus 1 and then possibly use the case induction hypothesis to prove the things. So you should not add it. You should somehow decrease it in terms of the sets. So say somebody is given this to us. So how can we do that? So in that case, I can use this one. So I can use define two things. I want to use axiom 3 here. Axiom 3 says that consider A be A1 union AN. So A is the definition that I have it. What about B? B would be AN plus 1. Good. In this case, I can now use axiom 3. It says that probability of A union B would be equal to, so probability of A plus probability of B minus probability of A intersection B. Good. Here, because we have this assumption, and we should refer to all of these essentially assumptions or definition. We have this disjointness. Because we have this disjointness, we know that A intersection B would be equal to empty set. Good. So if A intersection B is equal to empty set, it means that, so then again, now we are using axiom 2, and we should refer to all of this for disjointness because of the definitions in the theorem or, I mean, definition somewhere else or the axioms. So here, because of that, we know that this would be, in this case, would be 0. Then we know that probability of A union B is equal to probability of A plus probability of B. Now, what is A union B in this case would be this quantity. This would be probability of all the AIs. Correct? Because, I mean, we have A is equal to A1 to AN and B is equal to AN plus 1. And you take the union of these two, it means that essentially you are taking this one, and this is equal, so I will say from I equal to 1 to N plus 1. Good? Now, here, the good thing is that I could get, here I have the probability of A plus probability of B. Probability of B, of course, it would be just the probability of A n plus 1. Good. So I got the probability of A n plus 1 in this sum. Now I can use for A, I'm using induction hypothesis. I will say IH, that we talked about it. We knew that for N is correct. So for N, I could write this one, essentially sigma of AI, I equal to 1 to N. And then I have plus probability of AN plus 1. So if you have this plus this, then it means that this is equal to essentially sum of uh, probability of AI. I is equal to 1 to n plus 1. And that's exactly the things that we have. Good. And you see, all of these can be written. I mean, you can again probably use ChatGPT and ask. See, I'm not so sure that generally it is not that great in math formulas, but these are the things that you can write it down, and you should refer to all of these. And this. But the way, one other thing that you can do it, I will also like, especially for your assignments, because some of your assignments would be more theoretical things. I will generally recommend you that you are using LaTeX to write them. And I mean, when you write it down, I mean, you should write it down, but you can always, I mean, if you want to edit it further or something, that would be, I mean, good to use ChatGPT essentially. You can make it and you can just say, generally, one comment that it is very useful is say, revise minimally. Revise minimally, and then like your text, it just essentially make it much smoother. And that is, I mean, fine. But you should, again, refer that I use ChatGPT essentially to improve the writing, etc. But generally helps essentially to have much smoother things. And the whole idea of, I mean, ChatGPT, you can think about as a search engine that it see your sentence, you will see all the sentence in the world. I think this was one of the live that I had it with Moshe Vardi. He was actually mentioning a very good intuition that you can see in that one at my YouTube. And it says essentially, he was saying that in some sense, ChatGPT tried to find the best sentence. Some of them that we have in our mind, we try to improve it. But ChatGPT trying to find essentially the sentence in the whole world of the sentences, which matches the best your sentence. And that generally is better than my local minimum that if I, or those that I have currently in my mind. So even if you are a native English speaker, still it can essentially give you nice suggestions. So these are important that you will write in VS Code and LaTeX. The best thing is VS Code and also programming. That also generally the people are using VS Code. So that's a very important one. I think is a typical one that the people are using now, even for deploying onto cloud, etc. So VS Code is a good one, and you can do it both LaTeX and Python and C++ and others that you need for this course. And please write it down, and these are, you need to write it formally. And this one that I have mentioned, I mean, of course, you can see the text of this, the transcript of this, then it is mentioned essentially more formally. But you need to refer to everything. Good. So I wanted to go through one of them because we are seeing such kind of proof in this class a lot. And it is important that you are, I mean, very familiar with the proofs in these things. And in this class, without proof does not mean anything, because if you put the formulation, if you cannot use them correctly, essentially it means that you have done nothing. So it is super important, this one, that everything is math. And as I mentioned, a small mistake in these big companies in the math, it can cost them essentially millions of dollars. And this is very important thing. Good. Let's go to the next things. One thing that we are using a lot in this class is joint probability. Why joint probability? So for events A and B, the joint probability of A, B, generally, when we say A, B means essentially, A, B means somehow like multiplication. And multiplication generally means, in the set, it means intersection. So when we say probability AB here, we mean probability A intersection B. It stands for the probability that both events happen at the same time. And this is very important. Why? Because in the games that we played previous time, for example, we have lots of time, we have the simultaneous games. There are like two or more people, and this defined for more than two events as well, joint probability. We consider two players A and B. They are both of them. They are taking some actions, and these actions actually are corresponding to events. And then we talk about the joint probability that what will happen essentially for them, because we have two players. Generally, we have this kind of joint probability, and we are considering even more than like two players. You can define it. So that's super important when especially we talk about normal form game and the matrix representation. So here the probability of, again, when we say the joint probability, AB means that the probability that both of these events happen at the same time. So this is some example. So consider again H, because is HH, head, and B is HT and TH. What is the joint probability of AB? As you can see here, I mean, the probability would be 0. Why 0? Because A and B, they don't have an intersection. So, like it, in some sense, I mean, if two events happens, that means, I mean, like, what is the intersection of these guys? And if there is no intersection, it would be 0. So that is very important. So probability of AB means probability of A intersection B. And we are using it a lot in game theory. Another thing that we are using is independence. We say two events A, B are independent. If probability of AB, and again, probability of AB, whenever we say that, means that probability of A intersection B. So here, this is the probability of A intersection. Is equal to probability of A times probability of B. And again, as I mentioned, generally, this is the idea that when we have intersection, it plays very similar to multiplications. Union plays similar to summation or sigma. So here, it says that two events are independent if probability of AB is equal to probability of A times probability of B. And this you can define for more than essentially one event. Again, also we are using a lot of these notations in this class. As I mentioned, when you say AIs, if you don't put the indices, it means that generally there are some numbers from 1 to n that we are considering it. And I is between 1 and n, an integer between 1 and n. So a set of events AI is independent if, again, probability of their union is equal to multiplications of their probability. So let's see some examples here. So this is the two definitions that we already discussed. Independence, and more generally, I mean, if there are more than two sets, they are independent. So consider this example, a drug test example. So there is some company, I mean, some medical or pseudo-medical pharmaceutical company has done some tests essentially. I mean, for some drug. And they have tested essentially some success and failure and on men versus women. And these are the sample size that they have done it. They have, for the success on women was 200, on men was 1800. And the failure naturally was more in women and less in men. It means that this was something that worked better for men versus. So let's define two events. So one event is that, so event A, it means that a patient is a woman. So we consider like how many patients do we have here total? We have 4,000 essentially patients. And consider, I mean, so we have all these 4,000. And then the probability, I mean, the A event essentially is the case that this person that we are taking is, so we can consider that we have done this test and we want to do this probability space. Good. Now, so we consider, we choose one person, and that person is a woman. What is the probability of A in that case? So the event is that that person is a woman. What is the probability of that?
1/2.
1/2, because there are 2,000 women in general. Good. So that would be 2,000 over 4,000. The other one is that the drug fails. So what are the drug failure things? Again, sum it up. So for this person, the drug fails, there are 2,000 again over 4,000. That is the same figures. So both of them are half essentially. And then you want to say whether the event A and B are independent or not. So then we can just use the formula. So we knew the probability of A is half, probability of B is half. Now, what about the probability of AB? A intersection B. So in that case, what is A intersection B? So A intersection B. So it means that a patient should be a woman and the drug should fail, which would be this case, right? Which is 1,800. So that chance, that would be 1,800 over 4,000, which would be equal to 9 over 2. Now the question is that whether, now you want to see whether A and B are independent or not, then you just use the formula. So here we have 0.5 times 0.5, while the other side is 9 over 20. And these two are not equal. So it means that these two are not equal. And essentially, independent means that two things are independent. If one thing is happened, does not give any information about the other. If this event happened, didn't increase or decrease the probability of the other. If we know that one of these happened, it does not say whether the other event happened or not. Still, it would be hard actually if this is one of the things that, again, this is the intuition that I have mentioned, but sometimes in this probabilistic stuff, it is very crucial, and we are talking about it. Another thing is that whether something are correlated. If they are not independent, it means that they are correlated. And this is something it is not, and this is positive correlated or negative correlated. Again, this is one of the things, if you want, to know more about it, I have actually this live with Professor Aravind Srinivasan. He's a professor here. He's also teaching lots of probability stuff. And we had a live, actually, we are discussing about all this kind of intuition behind positive correlation, negative correlation. It's a very nice way you can get the whole intuition about it. If you want, you can take a look at to those lives at the YouTube that I mentioned. So, but there are lots of things that you can do. He's especially, Arvind is working on this area of probability theory and randomized algorithms. Good. So here, the best way is to use the formula. You can use the intuition, but the intuition sometimes actually may send you to a wrong place. The best way is to write the math and see whether it works or not. No other way else. And if you see something is hand wavy or something like this, if you read something, it means that that is not written well. Because if you write well, if you are in this business, everything should be very formal. Actually, this is also interesting when you work in the probability theory. Sometimes proving something formally can be very cumbersome and can be very technical and takes, pages of pages essentially to prove it. Because something seems intuitive, But I mean, until you write it down, all the details is not essentially something that you can claim it. And it is interesting. Sometimes I have worked with some researchers that, okay, this result is like you need to write lots of pages. And I mean, the result maybe is not that exciting. It's like intuitive. So in some sense, sometimes they may not write the paper just because it's just too much details that you cannot believe it. But sometimes it is like I'm spending a lot of time. It seems intuitive, but at the same time, I need to write the formal things for that, and that can actually take pages. So, especially in probability theory, writing the details is very important to make a claim. And sometimes it's better than don't claim, or if it's just too much details, maybe they don't want to write it at the end of the day. Especially if the final result is not that exciting. Anyhow, so these two are not independent because of this formula does not work. And that's the main way, that's the only way that you can formally prove something are independent or not. And again, if they are not independent, then it will be correlated. That would be the reverse of the, if two things are independent, it's independent, otherwise there is some correlation. Good. So let me clear everything. Some other interesting things about independence that we are talking about. So these are some independence is, I mean, it's very quite interesting things, and there are some interesting observations here. So consider experiment of essentially tossing a coin twice. So it can be head, head, tail, head, head, tail, or tail. Consider the event A, which is this, HT and HH, and B is equal to HT. Will event A independent from event B?
No.
So we need to use again the formula. What is the probability of A?
2%.
Oh, that's 0.5 because half of the time. What is the probability of B?
Order.
0.25. Now you want to say A and B are independent. You need to say, what is the probability of A intersection B? So yeah, it would be just they have the intersection would be HT. So it would be 0.25. Now, is 0.25 is equal to 0.25 times half? No. So it means that these are not independent. So the answer is no. Another example, consider A equal to HT and B equal to TH. Will event A independent from event B? Yes. Okay, no. Let's use the formula. Like no. Intuition is that's exactly the point that I want to say. Actually, you gave the best answer that why you should not use intuition alone, you should use the formula. That's the final answer. So what is the probability? So we are considering this case. What is the probability of A? The probability of A would be 0.25. What is the probability of B? What is the probability of A intersection B? So that would be empty set, and that would be empty set would be 0. So is 0 equal to 0.25 times 0.25? No. So it means that they are not independent. So what's the meaning of these two examples? That says that disjointness and independence, they don't have any relation. And that is, I mean, that was actually the mistake that you mentioned. That is actually very natural. But okay, two events are disjoint; they don't have anything. Why it should be essentially have any relation to each other? However, I mean, and again, intuition can be corrected. The correct thing is that actually these guys thought they are independent. there is something, this is a sequence. So for example, the fact that the first character of the A is H, it means that H essentially is H is happening. So yes, it is correct that HT and TH, they don't have any things. But when we say that the first event is H, it means that T didn't happen. So you can actually find the intuition, but generally that's the thing. If you want to just go by intuition, it might be dead wrong. You need to go with the formula. And then you can create the intuition out of it. But it is somehow more like after the fact. Unless, I mean, you worked a lot in this area, maybe you are better. But again, no one is prone of these issues, as I mentioned. And those people that I mentioned, they don't write some of this. They say, okay, it seems very intuitive. And I do all of this work. The people at the end say, okay, you prove some intuitive things. At the same time, you need to prove it. Nobody, I mean, you cannot publish a paper as I this is like you cannot use it. So in some sense, that's the thing that maybe like they don't want to write all of this work and at the end just prove some intuitive things. And so that's the thing that is interesting. Another interesting thing, if A is independent from B and B is independent from C, so this is actually, we want to say transitivity. So we know that A and B are independent, and we know that B and C are also independent. So the question is that whether A and C are independent or not. And of course, this is the one example, the thing that we have mentioned. Not necessarily, because just consider A equal to C. So in this case, A and B are independent. B and A are independent, but A and A is not independent. Like any set is not independent of itself, of course. I mean, again, why we can use the formula. What is the probability of A? What is the probability of A? And then what is the probability of A intersection A? So in that case, essentially, we should have the probability of A is equal to probability of A to the power of 2. And that happens only if A is empty set. Correct?
A is the sample space.
A is the event. So I mean, that's the thing. So A intersection A would be A. So it would be probability of A times probability of A. And this would be equal to this only if this is equal to, oh, and of course, 1 is also not. Yeah. So, if they are 0 or 1, then it is the case. Otherwise, it's the case. So these two are not necessarily correct. And is great. So let's talk more about this one. Another thing that we are talking about is about conditioning. So we say that two events A and B, if probability of A is greater than, if probability of A is greater than 0, then the conditional probability of B given A, the conditional probability of B essentially given A, it means that A happened essentially somehow. Then what is the probability of B? Is probability of AB in A intersection B over probability of A. This is again a formula, and we have this assumption that probability of A should be greater than 0, otherwise it is not. Good. So again, let's see one example quickly. So if A and B are events with probability of A greater than 0, the conditional probability of B given A is this formula that we discussed. Now, consider the same example that we had, this drug test example, the same numbers. Now, the same events, A patient is a woman and B drug fails essentially. And if we consider a random sample essentially, we can consider this has been done and we take one person. This event is that this person is woman. So what are the possibilities and what is the thing that it fails? So this is the space that we are talking about. With 4,000 people, we will take essentially one person out of them, and then this is the probability that we are talking about. What is the probability of B conditioned on A? So here we need to use the formula. What is the probability of AB here?
9/20.
Yeah, probability of AB, as we discussed, would be 9/20, right? And then here is probability of B condition on A. That would be over probability of A. And probability of A was 1/2. So that would be essentially this. And the same thing also would be probability of A because of the symmetry. Again, probability of AB would be A intersection B, the same thing that we discussed here. And over probability of B. But probability of B is also 1/2. For both of them, essentially. Again, it's the formula that way. So this is one important thing that given A is independent from B, what is the relation between probability of A intersection, A conditioned on B, and probability of A? So if they are independent, that's exactly the definition. Then I expect that the probability of A conditioned on B is equal to probability of A, because B didn't give you any information from. And again, you can see from the formula, if they are independent, then we know that this probability of AB would be probability of A times probability of B. Over probability of A. So in that case, this will cancel out. So probability of B condition on A would be probability of B. We can write it the reverse, and this means that essentially if they are independent, then the conditional probability on one, it gives essentially, does not change the probability. Yes?
If I remember correctly, we shouldn't rely on this definition of dependence because if probability of B is 0, that won't work.
Yes, exactly. So I mean, you can say that given A is independent from B, what is the relation between this one? And we have this condition that the probability of B should be not 0, because that was the definition that we had. I think that would be seen. And
so if we want to determine dependence, we should use the first definition.
Yeah. I mean, yeah, so this is not the definition. The definition is the original one. This is just some lemmas that come out of it. If we have this and the probability of this, then it is correct. That is correct, essentially, but this is not the definition. Good. Let's go. So we can also define, let me just. So let me go through this too quickly. So we can also define a conditional probability, conditional independence. So events A and B are conditionally independent. So you can have essentially combination of independence and intersection and condition. So we can use all of them. So we say that A and B are condition on C are independent if probability of AB conditioned on C is equal to this one. So you just, everything will be conditioned on C. And you can also define it for more set of events. You will say that these are conditionally independent given C, that everything that you will have written it without C, now you can add essentially conditioned on C. And let's see, this is actually one interesting example as well. So consider this case essentially that there are 3 events, A, B, and C. And A, B, and C, and the probability of A, probability of B, and probability of C is equal to 1/5. Probability of A, C, or A here means A intersection C actually. If probability of B intersection C is 1/25, probability of AB is equal to 1/10, and probability of ABC is equal to 1/125. Again, the probabilities are just some numbers that we are giving, some functions essentially. As long as they have these 3 axioms that we discussed, then that should be fine. Essentially, it can be any number. There is no need to be rational. I mean, some kind of rationalism or something for this one. It can be anything as long as there is nothing like sensible in some sense, as long as they satisfy that formula. So here, A and B are independent. Why? Because probability of A and B, say A and B, if you consider it, probability of A and B, both of them are 1.5, but B is 1/10. So these are not equal. It means that these two are, A and B are not independent. However, this is the interesting thing. If you consider A and B conditioned on C. So then probability of A over C, it would be probability of AC, which is 1 over 25, over probability of C, which is 1 over 5. So in that case, I mean, if you simplify, probability of AC would be 1 over 5. Probability of BC also, if you compute it, would be 1 over 5. And probability of ABC, if you compute it again, would be A intersection B intersection C over probability of C. That would be also, I mean, 1 over 125 over 1 over 5. If you compute it, that actually says that probability of A be conditioned on C is equal to probability of A conditioned on C times probability of B conditioned on C. So it means that if A and B are independent, doesn't mean that A or B are conditionally independent, and vice versa. Again, this, and in some sense that again makes sense. When you conditional or something, it means that something happened. We have some information. Now, if you have this information, then you know that these two are independent, or maybe they are not independent. So again, conditionally they might be independent, but not regularly, or vice versa. This is another, again, interesting thing about this. And we will continue next session.